Hello and welcome back to the fourth class lecture in my class on integration theory. So it's a new day and I've changed now my dark green jumper for another dark green jumper with a orange line on it to spice things up a bit. I've also decided to spice the lecture up a bit by completely skipping the remainder of chapter 1. So I realized that from a book writing perspective, it's natural to put everything about sigma algebras in one chapter, but from teaching or learning perspective, it might just bore you to death because so far you have no idea what the point is with this. We haven't been able to integrate yet. So I'm going to follow. It's even written in the chapter section 1.4 there, that the first time you read this you can skip. So what's lined up there, I'm going to briefly mention it so you know what it is about, and then we come back to it later in this course. So to connect with last class, what we were proving with lots of difficulties, let me see, was that the Borel sigma algebra is subset of but not equal to the Lebesgue sigma algebra, which is a subset of the power set and also not equal to that. And the most difficult part was to prove that these two were not equal. That's where we used all these counter functions and that. And I used two ingredients there, which I hadn't proven. And that's annoying. So one of the ingredients, which is that the Borel sigma algebra, when you take pre-images and images of if you have either continuous functions or increasing or decreasing functions, then they send sets through them without leaving the Borel sigma algebra. So the Borel sigma algebra is like invariant for those functions. And the other one was that if a set has outer Lebesgue measure 0, then it is Lebesgue measurable. So, but that's like a one-liner to prove. You don't need this bigger machinery to prove that. So I'm going to prove that single statement now. And then the other statement we need for this, it comes in later in this lecture. So, because we will discuss that when we discuss measurability of functions, that's chapter 2.1. And the rest I will leave for the future. So, okay, what is the statement here that we needed for this? It is that, so let me write this as a lemma. So if E is a subset of R, and the Lebesgue outer measure of E is equal to 0, then it follows that E is Lebesgue measurable. Now, how do we see that? Well, it's actually very easy, because what we need to establish is that for any set A, we have the following identity. But if the outer Lebesgue measure of E is 0, this is a triviality, because remember, this one we always get for free. This comes from this being an outer measure. The reverse inequality is also for free, because I remove the free. I write here OK. Now, this is a subset of E, right? I take an intersection. So if E has measure 0, then this being an outer measure, if I take a subset, I get something smaller. Smaller than 0 is 0, because we don't allow negative numbers. So here, this is equal to 0. Okay? So then, and this here, it is a subset of A. So clearly, this side is going to be smaller than that side, and hence this identity is okay. for all A, cumulus erratum dominicanus. So that was what we were supposed to be showing, right? This is the identity to check if this holds for all A, then E is a measurable set. Okay, so now that's done. Okay, I'll erase this one. So this property here connects with one of the three things we're going to leave out. So what we're leaving out is completeness, all right, where was I? Completeness, regularity, and translation invariance. Okay, so these are properties. Well, the last one is maybe more relevant. It's something that Lebesgue measure has, but at least the first two are properties that measures can have on certain sigma algebras. But I got this question from a student in the class, like, why do we even have two sigma algebras? Why don't we take the Lebesgue one and stick with it? And the real answer is actually, most of the time, 99.9% of the time doing integration theory, you don't care about the stupid sigma algebra. You just want the one sigma algebra, and we usually don't mention which one it is. So the fact that there are two, I mean, this is just natural. So some of the Borel sigma algebra is the smallest one containing the open sets. So that's a natural thing to look at. Lebesgue sigma algebra is somehow the biggest one because it, all sets satisfy. If a set doesn't satisfy this, then probably shouldn't. It doesn't gonna behave very well. So I mean, there are two natural definitions here. From a mathematician point of view, it would be unsatisfactory to just give you one and not give you the other when both are kind of natural constructions. It's very rare that there is actually any major difference when you integrate. When we're going to look at product sigma algebras later, this is going to have some advantages, because if you take the product of two Borel sigma algebras, you get a Borel sigma algebra of a higher dimension. That is not true for this one. On the other hand, this guy is going to have this completeness issue, which occasionally is a very useful one. So there's pros and cons here. Let me tell you what is completeness. It is, so this lemma here is a special case of completeness. Yeah? And it's really nice. I mean, if the outer measure is 0, then we know it's in our sigma algebras. We can use it without thinking. We don't have this for the Borel sigma algebra, so that's a drawback of the Borel sigma algebra. More generally, completeness is that if A is less than or equal to B, is less than or equal to C, and you have some measure, mu of A equals to mu of C, and you know that A and C are in whatever sigma algebra in generality we call the sigma algebra A, right? If you have this lined up, then it all follows that B is also in the sigma algebra. This is completeness. So it's some sort of, completeness theorem. So if you have a set B, which is squeezed in between two sets, and the two sets have the same size, so it's like sitting in the middle there, then it's also going to be measurable. So here, I mean, this set E, if the outer measure is 0, well, it's not really squeezed in between two sets, but anyways, it's So this is sometimes useful. Lebesgue measure on the Lebesgue sigma algebra has this property, and we're going to get back to that. Regularity. So completeness is in section 1.5. Most of the regularity business is in section 1.5 as well. But for the particular case of the Lebesgue measure, the regularity statement is the first theorem in chapter 1.4. So 1.4.1 is a regularity statement, and that is that we will have use for. So it's also a nice statement. So basically, again, if we have a sequence of inequalities like this, so one is smaller, this is in the middle, and this is bigger. And now we consider some mu of b. So usually, we don't know exactly which sets are in our sigma algebras. We can't just take an arbitrary Borel set. How does it look like? We don't know. Sets we understand is like open sets and closed sets. Okay, closed and bounded sets are called compact. So those are nice sets. So then we want to know, like, okay, if I have a difficult set, can I approximate it well with a nice set? And it turns out that if you do the infimum of mu of C, where C is open, okay. So this regularity business is only on Rn. On more general spaces X, we don't have open and closed sets most of the time. Of course, you can put some topology there, but anyways, so here this is in Rn. Okay, so then we have open sets, and then here we can do the supremum, mu of a compact. Yeah, I'm not going to talk too much about this since we're getting back to it. You can ask why is the compact sets on this side and the open sets on this side. But anyways, this is a property that a measure can or may not have, right? Turns out Lebesgue measure has this property. And actually most nice measures have it. So these measures are called regular. There's some twist to it there, but basically, essentially, this is it. This is being a regular measure. And there's a theory in there, like almost like all finite measures on Borel sigma algebra, I think it is, they are automatically regular, 1.5.6. But I'm coming back to this. But anyways, you should just be aware that there are statements like this that we're skipping now. The last thing that we're skipping, and this is like 1.4.2 to 1.4.4, I think I already mentioned that Lebesgue measure is translation invariant. Okay, that's fairly easy to prove. And also Borel sigma algebra is translation invariant. The Lebesgue sigma algebra is translation invariant in one dimension, in several dimensions. And there is one, the 1.4.5, which says, and this is interesting, if you have a measure which is translation invariant, so mu of x plus a is equal to mu of a for all x in Rn. Again, this concept is only in Rn. So if you have a measure which behaves like that, then basically your measure must be the Lebesgue measure. Let me check which sigma algebra that is on, just so I don't say something. Yeah, that's on the Borel sigma algebra. So that is a very interesting statement in itself, sometimes useful. So now you know it, we will prove it later. This connects also to, so if you can also do measure theory on group and on topological groups. So then this is like a group. If you have a set in a group, you can always multiply with some group element, and then that's like a translation. It will move the set somehow. And then you can think of what measures are invariant. And it turns out that there's always a unique measure with this property, except for some scaling. So that's called hard measures, and that's like chapter 9 in the book. So just for you to get a bit of an overview. But anyway, so all of this is very rarely needed And let's skip it for now and get to integration. I forgot to say 1.6 is even more technical. I'm not even going to mention what's in there, but we're going to need it in chapter 5. It's a technicality, so we will come back to that one as well when we do Fubini's theory. So if you thought I was going to tell you how to integrate, you got fooled, because first of all, before that, we need to decide which functions can we integrate, right? We have now discussed measurability of sets. We're now going to discuss measurability of functions. And then we can start integrating those measurable functions. Next class. So there are lots of theorems in 2.1. I'm going to summarize them with 3 key theorems, and then you read the rest yourselves. First, what does it mean for a function to be measurable? So, right, so we always start with a set X. We have some sigma algebra A, and for a long time now, we're not going to even care about who those guys are. They're just given from above. We call this a measurable space. That's this pair. A function on X with values in R, and okay, functions in this course are always from X into R. We're not going to integrate some multi-valued shit, or then you get into other types of integral. There are many other more esoteric integrals, Bochner integrals, and so on. But now the Beck integral, it's always just real values. We're just interested in functions. X can be how complicated as you want, but here we always have the real line. We call this a measurable function if f minus 1 of A is if the pre-image of any open set on the real line is in your sigma algebra. This definition, maybe it feels a bit weird to begin with, but it's not so bad, or it's kind of natural. So if this is our space X, right? And then our function f takes us to the real line. So we want somehow, so the open sets, they are nice sets. These are sets that we like to work with. Basically, it's an open interval, or a countable union of open intervals in the worst case. Now, what's the pre-image? That is all points in here that map to there. So if I take this red, then we're going to have some pieces here, which are all the points with values in there. So now that's a subset of my X, which I'm going to call f minus 1 of A. So the inverse set of A. This is not inverse in the technical sense of, you have a function that's invertible and then you can do the inverse mapping. This is just all points that map to A. So A is sitting here. In my example, it's just an interval. All right. So we want this red set here down in X to be in our sigma algebra. If that's true, no matter what open set you choose here, you're going to call F measurable. And yeah, it's not so weird, actually. If you think about compared topology, usually if you have a function F, or let's say G, from if X tau is a topology, so tau is then the collection of all open sets, then the definition of G being continuous is that if I take an open interval here, A, I look at the pre-image, so G minus 1 of A is going to be some set down here. And if for any open interval here, this set is open, then I'm calling my function continuous if you're taking topology. So you see, there's a complete analogy here. Usually when we construct mathematics, we have some collection that behaves nicely. And if we have functions involved, we want them to preserve this niceness, yeah? So nice sets over here, open ones should be transformed backwards through this function to nice sets over here, either be in the topology, so open, or be it here in the sigma algebra, so measurable. This is basic concept in mathematics, right? You call it homeomorphism, and it has different names in different branches, but it's like preserving of maps, some nice properties, what we usually after. Okay, so the definition is not so strange. Now, you might go like, okay, but why did he take just open sets here? It seems like he could have taken closed sets or maybe any Borel set or whatever. So that's the theorem one. There are many ways to define measurability, and I just picked one in the pipe. So theorem one says TFAE. Do you know this abbreviation? The following are equivalent. And we do F is measurable to F minus 1 of U is in A for all U in the Borel sigma algebra. Okay, so I could as well have started with saying that it should send Borel sets back to nice sets or measurable sets, sets in A. Or, so then I made it bigger, right? From open sets, you go to Borel. You can also go the other way and say that, okay, I mean, half axis, we saw that at some point. These are like the most, if you want to scale down the amount of building blocks you need to use to construct the Borel sigma algebra, you can actually limit yourself to semi-axis or half-axis. And it turns out it's sufficient to just check that the pre-image of a semi-axis is in your sigma algebra, then yeah. And there are a few other equivalent conditions here that goes down. I'm going to leave this for you to read yourself. This is basically a combination, so I write here just similar conditions. So this is 2.1.1 and 2.1.8. Right, so this is a combination of 2.1.1 and 2.1.8. Right, so let's look at how a proof would look like. So let's say if we have 2, then the pre-image of all Borel sets is in A. All right, but then clearly the pre-image of all open sets will also be in A. So according to my definition here, this implies 1. Now, if the pre-image of all open sets is in A, then clearly the pre-image of all half-axis, which are open, is going to be in A. So this is obvious. So the only thing we need to do now is to say that if we have 3, then any Borel set is automatically allowed as well here. So if we can prove that 3 implies 2, then we are done, because then this circle is complete, right? 2 implies 1, implies 3, which implies 2 again. It means that they are equivalent. Then you can just start with anyone and go the circle around and see them. How do we prove that 3 implies 2? So again, I've said this many times, the way you construct proofs here is a bit counterintuitive. So for me, I would say, okay, let me take a set U in my Borel sigma algebra and try to somehow get close to it or approximate it with this semi-axis. That's like a constructive approach to doing this. But that's not going to work because simply this guy is so big, we don't know how all the sets in there look. So we're going to do some sort of backwards argument here instead, okay? So D is going to be a collection of sets on the real line such that the pre-image is in A. I want to prove that this holds for all Borel sets, but I cannot. So the master plan here is to prove that D is a sigma algebra, okay? So A is a sigma algebra, so since the condition for being in D kind of relates to a sigma algebra, you can somehow feel that maybe it seems natural to think that D should also be a sigma algebra. Now, armed with 3 here, we know then that this is a sigma algebra which contains all semi-axes. And since Borel is the smallest sigma algebra containing all semi-axes, according to a theorem earlier, D must be bigger than the Borel sigma algebra. Therefore, if I have a Borel set, it's going to be in D, so the pre-image is going to be in A. Clever, no? Where did the book go? So the proposition you need for this is proposition 1.1.4, which actually talks about closed semi-axis. But okay, so how would you prove that? So, I mean, the sigma algebra generated by all closed semi-axis, you just prove that it contains open semi-axis, and then therefore that's a sigma algebra which contains the open sigma half-axis. And then you do it vice versa. Take the sigma algebra generated by the open half-axis, show that it includes the closed ones. So then you see that one, since in each case, this is like the smallest sigma algebra containing the building blocks. One is going to be bigger than the other and vice versa. And then you see that they are the same. That's basically how this proof 1.1.4 works as well. All right. Okay, so we want to show that D is a sigma algebra. Let's get to it. So we need to check 3 conditions, right? That we're allowed to take infinite or countable unions of sets without leaving the set, that we're allowed to do complements, and that the empty set is inside. Yes, these are the 3, right? So since the pre-image of the empty set is the empty set, which is in A, we see that the empty set is in D. Now let's do complements. So if A is in D, assuming that A is in D, I'm now going to look at the complement and think about how the pre-image looks like. Well, it's easy to see, just paint a picture, and you might as well take the complement of the pre-image of A, all right? Now this guy is in A, the sigma algebra A. Since it is a sigma algebra, you're allowed to take complements, so this whole bigger thing is going to be in A. Okay. So if A is in D, now we look at this object here, we see that it's the pre-image of A complement. This guy, since A is in D, it's going to be in the sigma algebra A, and then you're allowed to take complements. So this fellow is in the sigma algebra, the big thing, and then we conclude that the complement is also in D. And finally, so if A1 ... is in D, right, so if we have an infinite sequence of sets in D, then we want to prove that their infinite union is also in D. And how do we do that? We look at the pre-image of the infinite union. Now that's going to be the same as the infinite union of the pre-images of the respective guys. And again, the A case themselves are in D, which means their pre-images are in A. A is a sigma algebra. you're allowed to take the infinite union. And so this whole fellow is in A, which means that by definition, this thing here on the inside is going to be in D. And that's what we wanted to prove. So these were the three conditions that define a sigma algebra. The fourth one which is in the book, that you need to take infinite intersections as well. We prove that that's a consequence of the other three, so we don't need to check it. So I write cumulus erratum domenicus. Okay, so that was a bit of how these proofs run. Not very exciting, but it's a different way of thinking. Okay, I said there are three major theorems in part one. Here comes the second major theory. Right, sloppy version, take two measurable functions and do whatever you want with them. Sum them up, add them up, divide them, take the maximum. You're going to get a new function which is measurable. So this is like counterpart of, once you define continuity in analysis one, you want to prove that, well, I can create new continuous functions by just adding or dividing or whatever. You don't want to every time sit and think, oh, you made a new function or you added +1. Is this continuous now? You just want to know it. And this theorem tells you that, yeah, you can do what you want. As long as you have measurable functions, you're going to create new measurable functions. So, boring version of the same statement reads as follows. Okay, let's start with this. You can add up functions and still get measurable functions. You can multiply functions and still get measurable functions. You can multiply with a fixed number alpha, any real number, and still get measurable functions, which means that in particular I can multiply with -1 and get negative f, and then I can stick it in here and see things like f minus g. It's also going to be a measurable function. You can divide f by g with the catch that you're not allowed to divide by 0. How do we deal with that? Same as with continuous functions. Usually if you divide, rational functions, you just omit from the domain of definition the points where the denominator is 0. So same here, we're just gonna, okay, so this requires some terminology. A function on x can be defined on a subset of x. As long as x is measurable, that is fine. So if g is measurable, then the set where g of x is 0 is going to be a measurable set, because this is the pre-image of a point set x, and hence we can remove that from the big set x and still have a measurable set, right? So this set here is automatically measurable if g is measurable. Okay, so that's the domain of definition of f divided by g, and on that one, it is a measurable function.
Okay, so E, F.
The maximum of f and g is a measurable function. We use this notation sometimes for taking the maximum. F, the minimum of two functions is going to be measurable. So by minimum and maximum here, I mean point-wise, right? So if you have two functions, one function is this, the other one is this, the maximum is going to be this, and the minimum is going to be this, right? So in particular here, if you take the maximum of f and 0, you get the positive part of f. So that's always, well, the non-negative part. That's always measurable. Okay, now we scale this up a bit. So what's time? Given a sequence of measurable functions. We have f, so supremum of fk, k in n is measurable.
Infimum of fk is measurable.
So here, maybe mathematically there's not much going on, but for you to get your mind on it. So supremum of fk, or countable sequence, that's just taking the maximum, like you take the maximum of 2, but at each point you take just the supremum of all the functions, right? So this, if you always take a maximum of 3 functions, 4 functions, and of countably many functions. So that's preserved infimum as well. Lim sup is maybe something you haven't encountered before. What is this? This means actually taking the limit as, let's say, big K goes to infinity of the supremum as small k greater than big K of fk at then every point x. So because, okay, and the final one is like limit of fk is measurable where it exists. It's a bit similar like this guy division, right? So limit fk at some point x, k goes to infinity. It can either exist or it cannot exist. So here, what this says is that where it exists, that's a measurable set. And on that measurable set, this is a measurable function. But this is a problem often that we don't know that limits of a sequence of functions exist. Then you can always switch to this lim sup or lim inf, which is defined similarly. Because once I've defined sup, this function, right, for small k bigger than k, when I move big K upwards, then I'm taking a supremum over a smaller set of functions, meaning I get a potentially smaller number. So actually this is a sequence of functions itself, and you can call it GK if you want. And once you have a sequence of decreasing or non-increasing functions, completeness axiom of the real line, the limit exists. So this always exists, same with lim. So that's something you need to familiarize yourself with if you haven't done so already. Now, I need to rush and pick up my kids from the school, and the proofs here are boring and easy to see. I mean, it's written here. You see that at the bottom of my paper, these are the scribbled notes here. This is really not something deep, difficult going on. I'm just going to cut it out, go and pick up my kids. You read it in the book. And now we move on to Theorem 3. Sorry, I'm going to do Theorem 3 once I'm back, but for me, that's going to be, I mean, in my life, it will be tomorrow. In your life, it will be in 1 second from now. Okay, so I'm back today wearing a light blue jumper to match the color of my light blue eyes. And I was looking at these tiny lines here for the proof. There's actually some clever things going on. So let me highlight a few of the statements there in Theorem 2. If f and g are measurable, so is f plus g. So we are interested in the set of x such that f of x plus g of x is less than t, right? If we can prove that this set is in A, then we are done. And the only thing we know is that this set is in A if I remove the g for all t's and vice versa if I remove this. So how can we do that? Because, you know, if you paint this on a line, here's the number t, there are many different combinations. So f of x can be here, and then g of x could be here, and now the sum is less than t. Or we can have both of them here in the middle, or one could be even negative and the other one be beyond t. So there are so many different combinations here. So here they use a very clever trick, which is to note that there is a strict inequality here, which gives us some leeway to work with. So let's say this point is f of x plus g of x. Okay, so now there's a small gap here, which allows us to do the following. So let's take, I'm going to change color now. Let's take here a number. I'm going to call it q, which is rational. Okay? Such that this distance here is smaller than the gap here between the sum and t. Okay, so why am I doing this? Well, I mean, the rational numbers are dense and countable. So that's a very nice feature that's going to be used here shortly. So what we have is that our point x is clearly in is such that f of x is less than q and g of x is less than t minus q, right, by construction here. Vice versa, if I have any point x satisfying these two, and if I sum up f and g, I'm getting less than t, because here I have q and there's a minus q there, so they cancel out. So all points here are here, okay? And this particular point x that we started with is in here. But of course, if I take another point, like I said, there are many different combinations to get to this point. Of course, all of them are not going to be here. Now, here's where it gets really clever. So instead of just doing this, I'm going to put a parenthesis here now. And I do a union over all rational numbers in Q. So now, okay, I forgot to say, this guy is in A. This guy is in A. So then I'm allowed to take intersections because A is a sigma algebra. And I'm allowed to take countable unions. So at the end of the day, all of this is in A. And now the punchline is that if I'm calling this set, let me call it B. No. Yeah, I should just use a normal B in that case. Okay, so I meant to write equal to B, okay? It should be equal to B. Cannot fix it now, so you just have to remember equal to B. Sorry about that. Because it doesn't matter where f of x is and g of x is. You know, I can always find some rational number that's just a little bit to the right of f of x, such that yeah, so that this gap here is smaller than the gap from f of x plus g of x to t, and then that point is going to be in that intersection here for that particular rational number. So we need all the rational numbers, but there are countably many of them. So this is a countable union here. That guy is measurable, and that's what we wanted to prove, right? Very nice argument. Okay, then armed with that, let's take a look at this guy, f times g. Of course, here we could start trying to play some similar game, right? So if I have f of x times g of x less than t, then I could say that, okay, f of x is less than q, and then g of x, if q is close enough to that guy, then this is going to be less than t divided by q, stuff like that. But I think it's here we have to be careful a bit with the signs also. I mean, minus becomes a plus and stuff like that. So I'm not sure if this, I never walked this argument to the end, so I can't tell that it's going to work out. But anyways, it's always nice to look for clever alternatives. So that's what they're doing here. So we don't want to repeat this boring argument, or, well, it was interesting the first time, but now it's boring. Like driving a car. So let's do the alternative. So if f is measurable and g is measurable, and f plus g is measurable, because what I just showed, and now I can put a square on that. Yeah? Because when we consider, you know, f of x less than t, if I put the square here, that's the same. There's a minus square root of t there as well. But yeah, if f is measurable, then this here is a measurable set, and then that guy is a measurable set. So that's easy to see. Okay, so this is measurable. And then f square is measurable, and also g square is measurable. But now we expand this guy and see that f square plus 2f times g plus g square is measurable. Okay, but then I can remove him, and I remove him because they're also measurable. I'm allowed to take differences. So this guy is measurable. And yeah, I'm allowed to multiply with constant. That was the third condition, I think, so I can multiply away the 2 there. Also a bit nice. Okay, that's what I had to say about those proofs. So now let's go for the third important statement in chapter 2.1, which is a bit more technical than the previous ones. Well, before Theorem 3, it's actually written here some notes. So since I have a bit of space here on this board, let's do the notes. So what functions are the measurable ones? Well, just writing this up again, this is what we want to check if a function is measurable, whether this set is in sigma algebra. If f is increasing or non-decreasing, then this set is always a half axis, so it's measurable in the Borel sigma algebra, right? So if we do real functions, or functions on the real line, increasing, non-increasing, decreasing, non-decreasing, those are measurable functions just immediately. If you have a continuous function, then this set here, I mean, it's a pre-image of an open set. So you get an open set. That's in the Borel sigma algebra. So again, it's Borel measurable. And then, of course, also Lebesgue measurable, because the Lebesgue sigma algebra is bigger. So now we got actually a use for those facts there. What else are examples of measurable functions? Well, if I do the characteristic function of A, yeah, this is 1 on A and 0 elsewhere. So if you look at that, if t is less than 1, it's going to be the complement of A. Well, if t is less than 0, you get the void set. If t is less than 1, you get the complement of A. And if t is bigger than 1, you get the whole space X. So the possible level sets here is empty set, A complement, and the full space X, we can call it. We don't need to be on the real line here. So measurability of A and AC is the same thing, right? So we see that this is measurable if and only if A is measurable. And then we can start taking sums of this type. So if I do some Cj chi Ajx, j going from 1 to j, then it's the same logic. So when I look at this set here, I get unions of these guys Aj or their complements, finite unions. So if the Aj's are in the sigma algebra, then you're fine. So, okay, yeah, if all the Aj's are in the sigma algebra, this is always measurable. Going the other way, you have to be a bit careful because we could have a situation if two of the Cj's are the same, yeah, then I could write, for example, take this set E, which is not measurable, and then I do characteristic function of E plus the characteristic function of R minus E set minus. Well, that's equal to the identity function, right? Everywhere. So then I write it with 3 equality signs. So this is not measurable, but this is a simple, this is a sum of 2 of them, and it's 1 is a measurable function. So you can take sums like this where these guys are not measurable and still get something measurable, but only in the case that the Cj's are, you have multiple ones with the same value. So in general, that doesn't happen. But this is not super important to dwell on. The important thing is to give these guys a name because we will use them a lot. These are the building blocks of how we integrate. So such functions are called simple functions, assuming all Aj of the A. So a simple function has this form, and the Aj's are then supposed to be in your sigma algebra. I don't know what the book writes, but at least in my course, because otherwise you have to write measurable simple function. Maybe. Well, let me check out. All right, so the book says a function is simple if it has this form, or rather if it takes finitely many values, but that's the same thing. So I guess we have to write also that it is measurable if we assume that all of the Aj's are in A. It can still be measurable anyways, but not usually. Okay, now we're ready for Theorem 3. So I said these are the building blocks of when we want to build our integral calculus, which is natural, right? So this is, you remember we started with the, I'm just going to paint here. When we did the Riemann integral, we started with boxes like this, right? And we approximated our function. And this is actually a function of this type, yeah? So it's just that some constant values, and then your Aj's are intervals. And when we started this course, that's what in the introductory lecture, I highlighted that, you know, intervals is too coarse. We can't work with intervals because then we can't even integrate, you know, the characteristic function of the rational numbers on an interval. So from 0 to 1. So we need to go beyond the intervals and into this type of functions. But still, I mean, the whole Riemann integral construction is built on an approximation of the function you want to integrate, usually something continuous, with these guys. Hence, if you want to build a Lebesgue integral calculus based on these guys, we need some sort of approximation result, where we can say that, okay, if I take any measurable function, I can get sufficiently close to it by something like this. And that's exactly what we're going to prove now. Right. This is the statement. Given any function f which is measurable with values from 0 including infinity, so closed bracket here. We want to get arbitrarily close to it, but we don't like the number infinity really. It's uncomfortable to deal with. So we want to get arbitrarily close to it with simple and measurable functions, fk, but we don't want to include infinity in the range here, so this should be finite valued as well. It's an increasing sequence. This is nice because increasing means, sorry, non-decreasing, means that at every point x, this is non-decreasing, and then the limit exists. Here's a pointwise limit. Yeah? When you don't write anything else, this parenthesis x, it means take the limit at every point. Later in the course, we will consider more complicated limits in norm and so on. But for now, we just have this type of limit of functions that you looked at it pointwise. So that's what this means. So at every point, so the limit exists because it's a non-decreasing sequence at every point, and limit is the function f.
Jansson hämnas genom att kunna ge.
Okay, and I will explain this proof by just making a picture. It gets kind of messy to write down, but the picture, I hopefully will make it very clear. Okay, this is my function f. Here I have the number 1, here I have the number 2, here I have the number 3. I don't like that. Let's do it like this. Now what I'm going to do, I'm going to think of the lines here at 1, y-axis equal to 1 and 2. And then you look at the projection of this guy here down on the x-axis. So this I'm going to call A1, 1. And now we do the same here. And this I'm going to call A1, 2. So you get the point here with the indices. 1 is for, this is the first time I'm doing this, and then 1 and 2 here is related to, I'm counting them. There could be a third one also, but it's not because here this guy is above. So now what I can write, f1 is equal to the characteristic function of a11 plus characteristic function of a12. Which function is that now? It's this function. Okay? So making sure that we define this as open sets, so the set where you have strict inequality, so to speak. You will see that at this particular point that they kind of meet, actually the function value here is still 0, same here. So we have that this is strictly less than f. And now we're going to repeat this inductive construction. So now let's include a 1/2, 3/2, 5/2, and so on. Now this set here, we're going to call it A2, 1. This guy here is going to be A2, 2. This fellow, let me just write it right here. So A2, 2, A2, or A2, 3. That's this set, but it's down here, but it gets too messy too. Just write it. And then this guy that we already have is now going to be yeah, that's not my, yes, I did. A2, 3, A2, 4. And this fellow here is going to be A2, 5. Okay. So now if I sum all these ones up, I get something much bigger. I have to remember to multiply with 1/2. Then I go up here, to multiply with 1/2. Then I go up and then I take another half times this one. And I can create this function like this. How I write f2 equals to sum. J goes from 1 to infinity. 1/2 characteristic function a to j. Okay, so the sum to infinity doesn't matter because once you get above here, but what if this function now goes up to infinity? Then I will have infinitely many here because the aj's will never be empty, and that's not going to work out. Okay, so if it wasn't for that, you see that the sequence here I get, the second function I created was bigger than the first. So I have this property here. It clearly is so that whatever point you have here, sooner or later you're going to get closer and closer to it, because the numbers in F3, F4, and so on, it's going to be all the rational numbers which are where the denominator is 2 to the power of something. And that's dense, so you can get arbitrarily close. So it's also easy to see that we have this. Problem is that if I have infinitely many of these guys, then I'm not, it's not a simple function because we want finitely many function values. So I have to get rid of this guy somehow. Okay, so now this is a problem. So what if we do this? The first time, I actually only I stop when I reach the height 1. I don't go above 1. Then actually I can skip that guy, and this is my F1. The second time I'm going, I want to stop at 2. So I'm taking this fellow away, and I'm just stopping here. And then in the third time I construct a function, I stop at 3. I don't go higher than that, even if f does. If I were to do that, you would see that no matter how high a point is on f, sooner or later in the construction, you will be at the subindex here, bigger than that number, and then it doesn't matter. I mean, then you don't see this, that you kind of cut it off. So the fact that we cut off, so that would be putting a 4 here, right? I go until 4. So the fact that we cut off is not a problem here. We can also go all the way up to infinity like this. So then we get the general formula. Here would be f k be equal to a sum 1 over 2 to the power of k minus 1. Every time I make it final, I divide by 2, so this is the level 3 and so on. Now the question is, how high should we go? Well, if I'm at some big J here, little j goes from 1 up to big J, then the function value on the highest plateau, the AKJ, is going to be the sum of all of these guys. So it's J times that. So what we want, so we need to solve the equation J times 1 over. Right, so this would be the function value on the highest plateau. And then we want this to stop at k, so we want it actually to be equal to k. Yeah, this we can solve. So we just go to here, we put k times 2 to the power of k minus 1. So this is my general fk. And now I say, well, from the construction, it's pretty clear that these things are going to be fulfilled. Now, I built this function based on an intuitive construction, so I got this formula here, but this k minus 1 here is not necessarily, I don't think this is exactly how it looks in the book, but it doesn't matter, it works. control and make it a bit more beautiful. This is not the only way to do it, but it works. And that's how we approximate any measurable function with simple functions. And of course, okay, simple measurable functions also, because I didn't mention that, but I mean, if you look at this set, let's take A11. How did I define it? Well, it's all the points f of x strictly less than 1, right? So this guy is measurable. If f is measurable, this is measurable. So when we build these functions, these sets are always measurable, and then the functions are measurable. So measurability is also preserved. Good. There is also a chapter 2.2, which is a pretty pointless one. Let's go through that as well, and then we are done for today. Okay, so sometimes you have sets which are very small that we can ignore them, and it's nice to have a terminology for that. So take, for example, the function 1 over modulus x, right? So it is infinity, but only at the point 0. And if you want to integrate it or whatever, or let's take it 1 over x. Let's take a square root here, so then the integral actually exists from on a finite from -1 to +1, let's say. But there's this issue that the value is infinity, but it's only 1 point. But it's like, it's just 1 point. It's so small, it has measure 0, Lebesgue measure 0. So we don't care about that point. So in general, you can have properties on a measure space that at each point can be true or false. Like a function being infinity or not. Right, so property could be whatever. Space X could be a set of all. If we have any measurable space X, a sigma algebra A, and a measure mu, then you can have some property that can be true or false for all points. If it is true for all points, except those in the set E, which is so small that the measure is 0, then we say that property holds almost everywhere. So, for example, now I can make the statement that this function is less than infinity almost everywhere. Yeah, because this is actually false, but only at 1 point, that point is measure 0. So then we can ignore it. And now at this point, we can really just finish off finally that example. Okay, so I've come here to visit you from the past into the future. You remember this argument I had lined up here. I wanted to prove that the Borel sigma algebra and the Lebesgue sigma algebra are not the same. That I left undone, that there exists a set which is Lebesgue measurable, but not Borel measurable. Remember, the construction was this, G. I constructed a function G which was non-decreasing, and it was a bijection with a Cantor set. So, okay, we have here the interval 0 to 1. Here we have the Cantor set, which is very small, and we have this bijection G. And then I took a set E here, which was very ugly. It sends it into a subset of K. So G of E is now a subset of K. We know that now the Lebesgue sigma algebra is complete, or at least I proved in the beginning of the lecture that if a set has measure 0, then it's Lebesgue measurable. So this guy is going to be Lebesgue measurable because it's a subset of a set with measure 0. And what I used at the end of last class was to send it back using the function f. That was a slight technical mistake. We should instead note that we get back E by doing the inverse of G, or the pre-image of this set through G is giving us back E. This, in fact, I can replace this by F. But now to make it fit with our machinery, so it's better to write this identity like this, because now G is non-decreasing, so we know that it takes Borel measurable sets into Borel measurable sets. So if this was Borel measurable, then also E would be Borel measurable. So that's absurd. So this cannot be Borel measurable.